We're going to talk about compressible flow again today. Since pipes are so important to us in this class, I wanted to talk about compressible flow in pipes or in ducts, right? And again, these can be a very complicated problem, and you can get all kinds of different situations depending on the assumptions you make. So what we're going to talk about today is just sort of a little brief introduction for you to sort of see the kind of issues that can come up in compressible pipe or duct flow. So, and just as a review, we can, for an ideal gas, we can put density in terms of pressure and temperature, which means that to get the mass flow rate in ideal gas, you can just put MP over RT, which is the density, times the volumetric flow rate. But if we forget that gases are often compressible, it can lead to problems. So for example, here we've got a natural gas line, and let's say it's relatively long. Okay, you measure the volumetric flow rate, so with let's say with a nozzle meter or something, at the beginning of the pipeline, and then it empties at the end into a burner at atmospheric pressure. And so an engineer is trying to find the mass flow rate in the burner, so he uses this. What is his mistake? Will he over or underestimate the real mass flow rate, and how could he fix the problem? I want you all to think about this for 30 seconds, and then I'm going to call on someone for their thoughts. So I want everyone to think through this about 30 seconds. To a minute. All right, let's call on, how about Tyler Green, the greenest Tyler. Hey.
Hello.
So what mistake is this guy making?
I don't know.
Okay, so he's finding the mass flow rate through this, and he's using the volumetric flow rate that he measured back here, right, that, and the atmosphere over here, or the pressure over here when it gets to the burner. Those things don't match. Can you see why they don't match?
Is the flow rate going to change by the time it gets there?
Yes, it will. Because what will change by the time it gets there?
Well, the pressure will change.
Pressure will change. So it's not the pressure will change. So it's not even necessarily that the flow rate will change, though it will some. The most important thing is that the pressure will change. So he's using pressure from over there with the flow rate he measured right there. So the place where he measured the flow rate has a different pressure. And so the flow rate will have changed over there because pressure drops across a pipe. So that's his mistake, is that he doesn't realize that the pressure here where the flow rate was measured is going to be higher than the pressure here, where you use P atmosphere. So with that in mind, will this mean he over or underestimates the real flow rate? Let's say Tyler Krupp, and different Tyler. What do you think?
So the pressure at V dot right there is higher.
Mm-hmm.
So that means he should have used a higher pressure in that equation we're looking at. So I'm thinking that he overestimated the mass flow rate.
Probably yes. There's a little bit of wiggle room because, yeah, the volumetric flow rate might change, but the most common thing is he overestimates the mass flow rate, which means that they might not be getting as much mass as they need, and they might not be getting as much energy out of this burner as they think they should, and they don't know why. And the reason why is that they're not giving it a mass flow rate. So what are some ways?
Wait.
Yes.
Sorry, can I ask a question? So it seems like to me, if you're at the point, if you're at the left point with the V dot, and the pressure would be higher, right?
Mm-hmm.
So then you'd have a higher pressure. Did you guys say underestimate? Wouldn't he be underestimating then?
Yeah, he should be underestimating the real mass flow rate. Yes.
Okay.
Because it should, the real pressure at that V dot is higher than what he used. So that's
okay. Cool.
Okay, and this can lead to problems when he's trying to design the thing. Okay, so how could he fix this problem? Thoughts? Anyone? Open it up to the floor.
Measure the volumetric flow rate closer to the burner.
Yep, he could measure the volumetric flow rate closer to the burner. He could also measure the pressure at the place where he measured the volumetric flow rate. Or he could estimate what the pressure is there by estimating the pressure loss. He could also put a thermocouple to measure the temperature there. So anything that means he's measuring the volumetric flow rate at the same place where he's using the pressure and temperature. And there's a few different ways you could fix that.
Wait, why would putting a thermocouple right there help you?
Because you want to know what the temperature is, and you could assume the temperature is about isothermal along this. That probably wouldn't be a bad assumption, but the best thing to do would be to measure the temperature right where you measure the flow rate to put in there. Okay, and this is just an overview. This is just something I want you to know. I don't think I asked a homework problem on it, but we talked about orifice meters before. But when you're using orifice meters for gases, you want to slightly, this should be the formula you recognize, but you want to slightly adjust it. So you add an expansion factor there for when you're talking about gases which are compressible. It's about 1 for incompressible fluids. And for compressible fluids, you have to measure it or look it up. So I'm just letting you know that in your future endeavors, you may encounter this, and you should take that into account when using these flow meters for gases. All right. Any questions so far? Okay. So now we're going to look at a very specific flow situation. As I said, there's different situations depending, and you can derive different equations depending on the assumptions you make. You can assume for quite long flow with relatively lowish velocity, usually better to assume it's isothermal. We're going to talk about adiabatic flow. So adiabatic flow means no heat transfer. And this is generally best when you're faster. So it's so fast, there's no time for heat transfer. So the closer you get to Mach 1, the better this will be. And usually relatively short is better. And obviously you could insulate your pipe or your duct, and that would make it more adiabatic. things like that. But I just want us to think through it. Okay, so we've got friction happening. And in subsonic flow, friction makes pressure decrease, just like we're used to. And then in supersonic flow, above Mach 1, it actually does the opposite. It makes it increase. Okay, so supersonic flow pressure is going to increase along the thing. But let's think about next. So in general, if the pressure of a gas decreases, what do we expect to happen to, and how about people answer in the chat? I want to see people's answer in the chat for this. So when pressure decreases, what generally happens to density? Oh, there's no quiz. Someone says something about a quiz. Quizzes are canceled. No quizzes. Okay. Decrease, said people. Yeah. Less pressure generally means a gas will expand and its density will decrease. Which means then when the pressure is increasing, gas gets squeezed in, density increases. Okay, from what we know about conservation of mass, if density decreases, what should happen to velocity? This is adiabatic compressible flow going this way. Okay, I get a lot of increases. Yes, because if the density decreases and the mass flow rate has to stay the same, which we know it does, and the area here is constant, this is constant area. Okay, then the only way to keep the mass flow rate constant is if velocity increases. And so you can see that these should both, whether you start out subsonic or start out supersonic, if you go long enough, you'll get to Mach 1. Because when it's slower than the speed of sound, it'll start speeding up. And when it's faster than the speed of sound, it will start slowing down until it reaches Mach 1 and it's choked. Temperature. So again, this is a thermodynamics thing, so I don't necessarily expect you to know it. But if you have an expansion of a gas, what generally happens to the temperature? An adiabatic expansion of the gas. Temperature goes down. Incidentally, this is how refrigeration cycles work. The refrigerant goes through the cycle, it gets vaporized, it's a gas. The gas goes through like a valve, so it expands and makes the temperature drop. So it decreases. Right? So the speed of sound is related to the temperature. So how does the speed of sound go here? Or if the temperature is decreasing, what happens to the speed of sound? We saw that last time. Decreases. Finally, we've got...
I have a quick question about the speed of sound one.
Mm-hmm.
So we were talking about like how it's a lot, like something about it is a lot faster in water than it is in air.
Yeah, the speed of sound is much faster in water or in other liquids.
If temperature's a lot lower, then aren't like molecules a lot closer together and sound travels faster?
That would make sense, but temperature, a higher temperature also just means that molecules travel faster, right? So
Okay.
they may be closer to, well, so a lower density would mean they're closer together, but higher temperature means faster traveling molecules. So I would think they're more likely to bang into each other at higher temperatures.
Okay. Sounds good. Thanks.
Okay, so if the velocity is increasing and the speed of sound is decreasing, what happens to the Mach number, which is the velocity over the speed of sound? Increases, decreases, which is just as I said, at subsonic flow, get faster until it hits Mach 1 and chokes. Opposite at supersonic flow. This happens, incidentally, again, a thermo thing, because at choked flow, Mach 1 is when the entropy is at its highest, right? So it always, from whatever direction, it goes towards highest entropy.
Dr. Nickerson,
Mhm.
are all of these, all the values or all the words in red, are those based off of pressure decreasing or increasing?
It is based off of lots of things. So it's actually based off of a total energy balance, right? Or a force balance, because you've got, there's a couple ways you could derive this, but you've got friction that creates a force going back, and then you've got a pressure force going forward.
So it's simply as you go along a pipe,
This is as you go along
like
the
incompressible. Okay.
Yep, in the direction of the flow.
So I'm just want to clarify what we just talked about. So in supersonic flow, there's not necessarily head loss. It's as the flow increases, the pressure increases. There's not pressure drop as you flow for supersonic.
Yep, and so energy has to be being lost when we just look at the fluid, but if we look at this, it would seem that the energy is lost to friction, comes out of the velocity, out of the kinetic energy, and then it's not being transferred as heat outside. It's just going to increase the temperature instead. So there's a lot of different relationships in here that lead to this. The basic one would be like an energy balance or a force balance that uses the friction force and the pressure force. Okay.
And I've got a question.
Mm-hmm.
When would we have supersonic pipe flow besides a rocket engine?
I honestly do not know. I tried to look up papers about this and couldn't find anything. So most of the time it's going to be subsonic, yes.
Okay, that makes sense. Because I was trying to think of some petroleum factory being super efficient and really spitting out oil, but
yeah,
that makes
I
sense.
found something about supersonic compressors, which I guess is how you would get the flow supersonic in the first place, but I couldn't see what they were being used for. So I do not know. Maybe an aerodynamics engineering professor would know. All right. And again, maybe if you were a rocket scientist, there'd be some reason. I'm not sure. Okay. So some equations we can use for this. This one right here, and if I were you, I wouldn't bother to write this down. This will be on the slides. You can just refer to this. But this ratio here, which is a dimensionless group, by the way, if you look at it, it's the friction, it assumes a constant friction factor, which is an okay assumption. And for subsonic flow, you can usually use the Colebrook equation or the Holland equation, something like that. Okay, so F L over D is equal to this big function of the Mach number and 1. So at any point in the flow, there will be some Mach number, and you can find this, and the L star means the distance from that point to where it would choke. So even if the real pipe, it never chokes, this would be the distance it would take for it to choke. Does that make sense? Blake asked, will you post the annotated slides? I will. I've been posting the annotated slides for the last several since someone asked me to. Yeah. All right, so L star means this is how long we would have to go before flow would choke. That's what that means.
Can I ask a question? I'm just kind of confused about why does the fluid speed up as you go? Is it because the pressure is dropping?
The pressure's dropping, the density is dropping. And remember that the conservation of mass is okay, this is our conservation of mass, right? Because the density, the velocity, and the area, that gives us our mass flow rate. This is a constant area. Area isn't changing. So this tells us that if density goes down, which means that d rho, d density, is going to go down like this, velocity has to go up to account for it.
Okay, that makes sense.
Mm-hmm.
Okay, thank you.
Yeah, for mass flow rate to stay constant, which it has to, conservation of mass, if density goes down, velocity has to go up, and if pressure goes down, generally density will go down because just you're squeezing that gas less. It expands, density decreases. K is specific heat ratio. You can look it up. For air, it's 1.4. For air and other diatomic gases, so like nitrogen things. I believe that's technically at 25 degrees, and it might change with temperature, but generally we just assume it's constant. So it's 1.4 for air, for nitrogen, for oxygen, things like that. Okay.
Can I ask a question?
Yes.
So when calculating the friction factor, I'm confused how you would do that because the velocity is changing throughout the whole pipe. So like it's constantly changing.
Yep, the velocity is changing, the friction factor is changing. So this is technically average friction factor, which you would do at an average Reynolds number. Okay. For this class, I always just tell you assume a constant friction factor or blah. Or I believe on your homework, I asked you to first assume it's incompressible and find a friction factor and then use that. But yeah. This is the last lesson before the exam. The last lesson of them all. Isn't that, whoa, momentous. Okay. All right, and here's some other equations that are similar. And so here the star means the same thing. It means whatever this thing is at Mach 1. As I said, all of these depend only on K and the Mach number. So for air, in the appendix of your book, table 16 actually gives you some of these values for different Mach numbers, like 0.1, 0.2, 0.3, etc., which sometimes can speed stuff up because it's just always going to be the same if you have the same K and the same Mach number. Okay, how do we use these equations to solve the problem? We're going to do one problem. It's going to be the same problem that's on your homework, and we're just going to talk through how it's set up here in class. So I wanted to find some kind of application for compressible flow. And one that is interesting is pneumatic conveying. So it's used for powders or other solid things. And so what we do, we have some pressurized. So this one is using it for little pellets, and it's just, okay. You got pressurized flow. You can have it, if it's dilute enough, it can just be flowing along. If it's heavier, you kind of need to do it in pulses of pressure. But That's the point, is we use this pressurized gas to move this solid along. My father's a chemical engineer, and I talked to him about a time he was buying a pneumatic conveying system for his plant. And he sent me this message that the pneumatic conveying system company sent him. Apparently they have used this for gunpowder and live chickens. So you can use this to move a lot of solid things around. Okay, so now one thing though is if velocity can get too high, it can corrode metal, especially if it has some kind of powder in it. Like what if it has gunpowder in it, for example, and it's going real fast and the powder will just scrape against the sides. So if it gets too fast, it's bad. Let's get some thoughts about what you might do to keep it from getting too fast.
You could maybe increase the diameter.
That is a good answer, right? If you increase, remember, because we said the density and the velocity and the area are all related. So you can increase the diameter to make it slow down. And they call this stepping. So after a while, it'll get wider. Okay, what will happen if the velocity gets too slow?
You don't get any flow?
Yeah, it has to be fast enough to carry whatever this powder is, right? Or whatever the solid thing is. If the velocity gets too slow, it'll just drop. So the gas could still be gently trickling along, but whatever the solid thing is won't be flowing. So we're going to do a problem about this. So we're going to take sugar, and I looked up on Engineering Toolbox the carrying velocity of sugar, found it was 30 meters per second. So let's assume we want an initial velocity of 40 meters per second. We're going to assume that we can use adiabatic flow, and we can use those same equations we found. This is not a great assumption because in actual life, you need some more pressure to carry the solids along. So that's going to create a bigger pressure drop, but we're just going to take this as a rough estimate for educational purposes. Right, so at what length should the initial pipe be stepped to make sure it doesn't speed up beyond about Mach 0.3? And I gave you a constant friction factor. I want us to just think about this for a bit. We've got 20 minutes left. We might have time to go over the second homework problem too. So let's think about this. I'm going to give about a minute. Thinking of the different equations we had, let's try to think how we might do this. For this one, no, you shouldn't. Oh, Connor just asked whether we'll need a solver, and I said, actually, you should not need a solver for this. Let's start with just, of those equations I gave you, was there one that had length in it? That's probably what we should use. Yeah, it was F L star over D is equal to some function of the Mach number, right? And what that is, remember, is the length between when the Mach number equals whatever and when it would be choked. So in this case, we've got 2 points. There's the beginning when the Mach number equals, you would need to calculate it. Need to find the speed of sound in air at 20 degrees and find the Mach number. And then the second one, I said Mach number is 0.3. Right? Yes, F is friction factor. Right? So call this.
Can we assume that? Oh yeah, this is like what Rankin's question. Does it increase linearly? Like if you start at 0 and then go to 1, would Mach of 0.3 be at 0.3 of like the distance?
No, not necessarily.
Okay.
But you know what we can say? So call this like L star 2 and this L star 1. So this means the distance you would have to go from that point to get it to be choked. So how do you get so from that, what would the distance between the two of these guys be?
That would be the distance before we have to change the diameter.
Yeah, yes, exactly. And that's what we're trying to find, the distance before we change the diameter, because we don't want it to get any faster than Mach 0.3. So as I said, this is L star 1, the length it would have to go from point 1 to be choked. And this is L star 2, the length it would have to go from point 2 to be choked. So what is the length between 1 and 2 then? Terms.
It's L1 minus L2.
Okay, L1 minus L2. L is equal to L star 1 minus L star 2. Thank you, KK. Like that.
I have a quick question.
Yep.
So if it says we don't want the air to speed up beyond Mach 0.3, so is the 0.3 at the very end of that first line of pipe?
Yeah, before it gets stepped up.
Before it gets stepped. Okay, cool. Thanks.
That's just how I decided to set it up. I think it makes sense. Okay. So, you know L star 1 minus L star 2 is L. How do you get L star 1 and 2?
Using that equation.
Using that equation, right? So you could get F L star over D at Mach 1. Like you'd have to calculate the Mach number there, and then you could find it. And then you could get same thing at Mach 2 like that. Using that big equation. Or at Mach equals 0.3, you can actually look it up in the back of the book. Mach 0.3 is not choked, Nicholas. Nicholas, what is the definition of choked flow? We talked about it last time.
Mach 1?
It happens at Mach 1. It's when it can't speed up anymore. It's reached Mach 1, can't go any farther.
Okay.
Mm-hmm. Alrighty, so you can find both of these from the Mach number. And since F and D are the same for both of these, if you find this minus this, what could you multiply this by to get the length?
Sorry, my Zoom is cutting off the bottom half of all those equations that you're writing.
No. Is that better?
Yeah, a bit.
A little bit? Okay. All right, so we just took FL over D minus FL over D, which you can calculate out from the Mach numbers. What do I multiply this by to get the length?
I was just multiplying by diameter over friction factor.
Yep, exactly. That is a weird D. It's the weirdest D ever. Okay, there you go. And that'll just get you the length. So it's actually pretty straightforward. Since we have 10 minutes, let's talk about the other problem we're going to have on the homework. So the other one I say, or any other following questions on this first? Okay. So this problem, so that one I gave you what the Mach number should be at the end, and I gave you what the flow rate is at the beginning, which you can use to get velocity, which you can use to get Mach number at the beginning. So you know the Mach number at the beginning and the end. But what if, so in this one, I tell you, you've got a pipe, and I actually give you the length. I give you L. And then I say at the beginning, I give you flow rate, pressure, and temperature at the beginning. And I say part one, find what the pressure drop over this length will be, assuming it's incompressible. So I'm going to call on someone to just tell us what you would do if this was incompressible. Brooklyn?
Yeah, if it's incompressible,
Mm-hmm.
you'd probably just do Bernoulli's equation.
Mm-hmm. Incompressible. Find delta P. Okay. So yeah, you could just use Bernoulli's equation, which just tells us that P2 minus P1 plus, if it's incompressible, what do we assume about the velocity?
And that the velocity is the same.
Velocity is the same. So what happens to this one?
It goes to 0.
It goes to 0. And is there any height change?
Nope.
Nope, we're assuming a horizontal guy, and that equals, what does that equal?
That would equal 0 as well.
Well,
are we accounting for losses?
Yes, we are accounting for losses.
Okay, then it would equal negative pressure loss.
And negative pressure loss. And then you would just get pressure loss from, how would you get pressure loss?
The pressure loss equation, it's let me remember it. It's friction factor times length over diameter times 1/2 rho v squared.
Yeah. Yes. Yeah. So I would, yep, I usually write it like this, but like that, but the way you said is also right, of course. Okay, so you just do that. And you do that, and how would you find friction factor?
You can use the Kohlberger-Holland equation.
At Kohlberger-Holland, you already know V dot, so you can get a velocity, just get Kohlberger-Holland. Okay, so first I just asked you to do that, and then I say take the F you used from that, and now we're going to assume it's compressible and adiabatic. So let's say it's a very well insulated pipe here. So now I want you to find V dot 2, P2, T2. That's what I want you to find now. So this is, so how do we think we're going to do this? Anyone? I'm opening up the floor to anyone to think, how do we think we should start doing this?
Don't we have all those equations that you gave us on the slides?
Yes, Connor, we've got all those equations. We've got all of these equations. So these equations all use star, which is what the property is when it's choked, when Mach equals 1. We don't know that. We could try to calculate it somehow, or we can just get rid of it. How should we do that, do you think? Okay, how do you think we will get rid of all of these star ones in these equations to figure out how all these properties change from point 1 to point 2, which is like there, 1 to 2.
Would you divide one equation by the same equation?
Yeah, you can divide the equations by each other. Who said that?
Rankin did.
Rankin, hey, yes, you can do that. You can divide by those equations by each other. So you can find P over P star at Mach 1 over P star at Mach 2. And that'll get you P at Mach 1, or I keep saying Mach 1. I shouldn't say that because usually when you say Mach 1, you mean Mach equals 1. I mean the Mach at point 1. The Mach number at point 1 is what I mean. Like that. And you can do that for all of them. Okay, but in order to do this, the first thing you got to do is you need to find out what the Mach number is at point 1 and at point 2. So let's talk about how you would do that. And then you can find all of those things, and that's good. But first, we want to find Mach at point 1. And we have the volumetric flow rate and the temperature and the pressure there. So what should we do?
Use the ideal gas law.
Okay. So use the ideal gas law to get the property. Well, we have the volumetric flow rate and we have the area. So how would you get the velocity? I went ahead and just told you what that was.
Don't you use the properties to first find the speed of sound and then use volumetric flow rate divided by area to get velocity, and then the velocity over the speed of sound is the Mach number?
Yep. So just get the speed of sound from the temperature, which there's an equation for it. You can also look it up usually. Okay, so then get the Mach number like that. So get that at the beginning, and then you have the length, and you can go backwards from the length to figure out what the Mach number has to be at the end, and you might need to use a solver for that. Okay.
Wait, how did you say we get the length?
Well, I tell you the length of the problem.
Oh, okay.
Yeah. So you can go backwards from what we did here. And the length in this whole thing, you should be able to get what FL over D, FL star over D has to be at 0.2. And from that, you can get what the Mach number is at 0.2. You might have to use a solver. Okay. And so once you, from length, find to find Mach number at 0.2, and then you can use all these equations to find how the pressure and the density and the temperature changes. Rankin says, are we always going to be able to use the ideal gas version of speed of sound? In this class, we always assume ideal gas. And ideal gas is mostly going to be a good assumption for air and carbon dioxide and nitrogen, basically most of the gases we care about. It's pretty much ideal until you get really cold or really, really high pressures, and we don't really, so we just assume ideal gas. You are going to assume ideal gas basically until you get to thermo. Okay, so that is how I would do the homework. Again, I just sort of want us to have practice doing a kind of compressible flow problem. There's all sorts of other kinds you could do. Thoughts, feelings?
So you said you wanted us to practice these specific types. Is that the only stuff that might appear on exams, or should we?
Yes. Nothing that I don't give you on the homework is, so, and in fact, it might, so yes, this could appear on the exam. I won't ask you on anything in the exam, something I didn't put on the homework and we didn't cover in class.
All right, thanks.
Yeah, and the entire homework is these two problems, that first one and this one. I will also, the exam will have conceptual stuff about compressible flow. I'll ask you, for example, so I could ask you at subsonic adiabatic compressible flow, what happens to the Mach number as you go along the length of the pipe? And the answer will be, it will increase until it until it gets to Mach 1 and it's choked. That would be the answer. Okay. All right, and that, yes?
Could you go back to the length slide? When were you solved? Yeah.
Yeah. Oh, this one?
When were you solved for the length?
Yeah.
Yeah. How did you get the two length stars?
Okay, I did not get them directly. Okay, I just knew, but F length star over D comes from this equation right here. So this equation right here gets you F length star over D.
Yeah.
All right, so you could get F length star over D for the two Mach numbers. It gets you this. And then if you have F length star over D, F and D are the same. So then you multiply by D over F to get L.
Okay, so you wouldn't actually use length star in either of those.
No,
You'd actually.
Well, I guess like you could, because you could find F length star over D and then multiply by D and divide by F, and that would be length star. So you could do that.
And this L from this part is the length at which the stepping needs to happen, right? It's not the total length.
Yes, this will be the length at which the stepping needs to happen, which will be, I mean, that'll be the total length that you get. That will be the length of this pipe section that you end up with. That's where you'll stop the pipe and make it go wider. But no, it won't be length star. Length star just doesn't show up at all. We just kind of got rid of it for convenience. I feel like you all have sad faces because you feel like this is very confusing. And I agree that we did not spend very much time on this. So I don't really expect you to have a deep understanding of compressible flow at this point. I just wanted us to touch on it lightly, so you could see the wonderful world of fluid mechanics that is out there. Now, on Friday, we will review for the third exam. And the reason I do a third exam at the end is because I want the final to be comprehensive. So that is what we're going to do. But for then, in the last, yeah, all right.
Could I ask a quick question, Dr. Nickerson?
Yes.
I guess it might not. Could you? So we kind of derived these equations, just kind of our basic understanding of how they worked based off of, whether density, velocity, temperature will be increasing or decreasing. But I didn't quite understand when we were going through that how we got those.
Where they came from.
Yeah.
Because I didn't talk about where they came from, really, because it is complicated. If you are interested, your book, it's called Flow, is what it's called. Adiabatic Flow with friction, 12.6 in your book, and it goes through everything. I decided to just skip over and kind of tell you conceptually what happens.
Yeah.
So
I was thinking more that first slide where we had the table that we were filling in, and we were examining what was happening to density and velocity and temperature and whatnot. It never really clicked where we're getting the decreasing or increasing.
Okay. Well, I was just sort of trying to talk through what I think it is intuitive, though again, the actual equations used to derive those equations are in here, and it goes through and talks about how it puts together the energy balance and the force balance, and all of these relationships pop out of there. Okay.
Okay.
And also those equations I showed you, if you put in Mach numbers, you should see that if you put in a Mach number less than 1, pressure will go down. And if you put in a Mach number greater than 1, pressure will go up, and et cetera, all that stuff. You can see it in the equations if you try.
Right.
When I tried to talk through it, I just sort of tried to talk through logically, which is that the subsonic part should make sense to us, so does it make sense to you that at a lower pressure, we usually get a lower density?
Yeah.
Okay.
Yeah.
And it should make sense that a lower density makes the velocity increase. Does that part make sense?
Okay. I see it. And then we talked through temperature based off of what generally happens to expanding or contracting gas.
Yeah.
And then speed of sound, Mach. Okay, they're from those
Right.
equations. I just missed that.
Yeah. So like the momentum equation and the energy equation and all of that stuff that was used to derive the fact that pressure goes down and up. That's in your book, and you can look at it if you're interested. And from that, we just sort of talk through it logically.
Right. Okay, cool. I think it actually clicked now that we went through that the second time. The first time it was just like, where is she getting this? I don't know.
All right.
But
well,
I got it.
I'm glad.
Thank you.
I try.
All right.
And then
Thanks, Professor.
And then I have a question on that second homework problem. Could you go back to where you were writing out the steps?
Yep. That one. Okay.
Yeah. Okay, so I understand how to find the Mach number at 0.1 because we can find the velocity, and then it's just velocity over the speed of sound there. And we can find the speed of sound because it should just be the speed of sound in normal air, right?
Yeah,
so we could calculate that, or just use
calculate it as this if you want, but you can also just look it up. It is at some temperature. It's at 500 K or something. So it's not exactly room temperature, but You can always
Okay.
look it up still.
Okay, so we can use that to find the C, and then we can use the V dot to find V, and then use that to find the Mach number at the start. So I understand that part. But then the second part, so from the length, find the F L star over D.
Yeah, so I
Could you
said,
explain that part?
all right, so I said we could go backwards from the last part, from what we did on the other one. So on the other one, we said that the length is equal to F L star over D at 0.1 minus F L star over D at 0.2 times D over F. Okay, so once you find the Mach number at 0.1, the Mach at 0.1, you can find F L star over D at 0.1, right? Okay, and so then you can use that equation, which we used in the last one, to find F L star over D at 0.2.
So that's the part that I see how to find the F L star over D at 0.1, but what do we do in order to find it at 0.2? Like, how do we make that jump?
We know the length. And we just said in this one that we can find the length in between the 2 points from the differences in the FL star over D.
And that length, so the length in this one is the length between being the Mach number 1 and Mach number 2. And in this second problem, then the length.
The length I just give you. So it's still the length between Mach number 1 and Mach number 2. But the difference is in the first one, you knew what Mach number 2 was, but you didn't know the length, and you found the length. And this one, you know the length, and you don't know what Mach number 2 is. So you just go backwards.
Okay, so then that's what lets us solve for that F L star over D at 0.2. And then we would just use a solver to find the Mach number, because it's kind of implicit with Mach number. There's not really a nice.
It is implicit with Mach number. You can, as I said, there is a table in the back that gives it for like Mach number 0.1, 0.2, 0.3, so you can check whether it's close to one of those, but it might not be, so you might need to use a solver. So now you found Mach 2. Okay, and so then, after you've done that, you can use all of these ratios, because you can find what each of these would be at Mach number 1 and Mach number 2. Put them over each other to get the ratios of pressure, temperature, density, etc.
Okay, I think that makes sense. So this is the last thing. So on this one, where are you getting the P over P star at Mach 1 equals? Oh, so all of these are then equal?
They're not equal because...
I mean, I guess I should rephrase that. So P over P star and V over V star and rho star over rho are all equal to that same quantity, right?
They're all equal to the same stuff. They'll obviously, the part on this right side will change when the Mach number changes.
Okay, so that's why we solve for Mach 2 first, is so that now we know what that right side, we can calculate the right side of that equation for Mach 1 and for Mach 2.
And then put them
That's
over
what lets us
together.
find P. So, and then I guess, are we solving for P or P star?
So P star is the pressure when flow is choked. And so we divided by this so to get rid of that, because we just want the pressure at 0.2. So just call it 0.2. We're trying to find P2. And you know P1, I told you what it was at the beginning. We're trying to find P2.
Okay, that's helpful.
Okay. All right, I have to go to faculty meeting. See you guys later. I will post the notes in the video for this. Bye-bye.
Thank you.